Hi class, today we're going to be talking about complex numbers and the quadratic formula day 2. So the warm-up for this lesson is just simplifying some of these expressions involving complex numbers. Remember in the first one, when you are simplifying, you want to make sure you combine the like parts of the complex number. So first, since you're subtracting two complex numbers, remember that you want to subtract both terms of the second number. So you've got to distribute that negative sign to both. So it becomes plus 3 and minus 3i. Okay, and then combine your like terms. So negative 2 and positive 3 would make positive 1. 7i and negative 3i would make positive 4i. And that would be the simplified answer. Okay, the other one, you want to multiply each of these terms by the 4i in front. So 4i times 3 is 12i. 4i times 10i would be positive 40i squared. Remember, I squared always equals negative 1. So we can replace I squared with negative 1, substitute that in. And you have 40 times negative 1, so that becomes 12i minus 40. Okay, and that's simplified. However, if we're going to write it in a plus bi form, we're going to start with our real number first, negative 40, plus our imaginary number. Okay, so that's in a plus bi form. Okay, the next question asks you to discuss with your partner. Obviously, you don't have a partner, but think about what is the purpose of the quadratic formula? What does it tell you? When we use the quadratic formula, it's another method that solves a quadratic equation. In other words, it finds the answers for x when it's equal to 0. It finds the zeros of the quadratic. It finds the roots. It finds the x-intercepts. All those mean the same thing. Okay, so let's take a look at this next example. It says solve x squared plus 3x plus 3 equals 0. Can you factor it? If not, use the quadratic formula. So remember, when you're factoring this, you're trying to find two numbers that multiply to be positive 3, like 3 times 1, that also add up to 3. Well, 3 plus 1 doesn't equal 3, so this is not factorable. So I have to use the quadratic formula to find my zeros. So quadratic formula, find your a. A would be positive 1. B is positive 3. C is positive 3. So if I use my three musketeers, negative b would equal negative 3. B squared minus 4ac would equal 3 squared minus 4 times 1 times 3. So if you calculate that number out, 9 minus 12 would equal negative 3. And last we have 2a, that's the other musketeer. 2 times 1 is 2. Okay, so if you plug it into our formula, these three numbers, we have x equals negative b, negative 3, plus or minus the square root of b squared minus 4ac was negative 3, all over 2a, which equals 2. Okay, so we get an expression with a negative under the square root. Well, hey, now we know what to do here with negatives under the square root. This ends up being an imaginary number. Remember, if we're going to find our full answers, we're going to break up that square root into square root of 3 times square root of -1. And remember, square root of -1 is the same as I. So my answer for x will be -3 plus or minus the square root of 3 times I is not under the square root, all over 2. Okay, I'd like you to try to plug this equation into your graphing calculators and take a look at it. When you graph it, you should be getting a graph that looks something like this. Okay, and you'll notice when you graph that equation, there are no x-intercepts because our roots, our solutions, are not real numbers. Whenever you have an imaginary number in your solution, you are not going to have x-intercepts. So I just kind of explained number 7 there, so if you can write that out. There are no x-intercepts in the graph above because the answers we got in number 5 were imaginary numbers. Okay, solve each equation and simplify your answers. Find the zeros. Okay, so to solve these, I'm going to start with number 8 here on a separate sheet of paper. Okay, to solve this, remember you have to make sure first that your equation is set equal to 0. So you want to add 5 to each side so that all the terms are on one side. 8a squared plus 6a plus 5 equals 0. Okay? Once it's in that form, then you can use quadratic formula. A will be 8, b will be 6, and c will equal 5. Now do the three musketeers. Negative b is equal to -6. b squared minus 4ac will equal 6 squared minus 4 times 8 times 5, which equals -124. And 2a equals 2 times 8, or 16. Okay, now we have our three musketeers. Let's plug them into our formula, quadratic formula. X equals opposite b plus or minus the square root of b squared minus 4ac, all over 2a. Okay, so here we have this. Now we want to fully simplify our answer. We've got a negative under the root. Also, I believe we can break down square root of 124. If we do the prime factorization of that number, I know 124 is the same as 2 times 62, and 62 can be broken down to 2 times 31. So we've got 2 times 2 times 31. 31 can't be broken down anymore. So if we rewrite this, we have -6 plus or minus the square root of -1, because I have a negative, times 2 times 2 times 31, all over 16. Okay? So now remember our rules for simplifying square roots. I can pull this out, that equals I, and this is a pair. So remember, pairs go outside to play. This one stays underneath. So when you pull out this, I have an I and I have a 2. 2I goes on the outside, and square root of 31 stays underneath. Okay, now we can reduce this even more because you'll notice each of these terms, you have 3 terms here, can be divided by 2. They have a common factor of 2. So if you divide each term by 2, you can simplify it more. -6 divided by 2 is -3. This term divided by 2, the 2's would cancel out, so you just have I times the square root of 31, or square root of 31I, it doesn't really matter the order, over 16. Now, if I were to split up this answer and put it into a plus bi form, I would separate out these fractions. This is like saying negative 3 over 16. Oh, I'm sorry, I forgot to reduce 16. Let me go back. I forgot to divide 16 by 2. 16 divided by 2 is 8. Oh, undo that. I want to be in the right part here. 8. Okay. So if you separate this out into a plus bi form, that's the same as saying negative 3 over 8 plus or minus square root of 31 over 8 times I. And that is our simplified answer. Okay, next question, number 9. Okay, same thing here. We got to get all our terms on one side of the equation. So I'm going to move this x over to the other side by subtracting it. And we have 10x squared minus x plus 9 equals 0. Now I've written it in standard form and it's equal to 0. So now I'm ready to use quadratic formula. My a will equal 10, my b will equal negative 1, and my c will equal 9. Three Musketeers, negative b, negative of b, the opposite of b is positive 1. Because I'm doing a negative of negative 1, so that equals positive 1. B squared minus 4ac will be negative 1 squared minus 4 times 10 times 9. So that's like saying positive 1 minus 360, so that will equal negative 359. 2a will equal 2 times 10, or 20. Okay, so now let's plug this all into my quadratic formula. Negative b is positive 1 plus or minus square root of, our discriminant is negative 359. That's b squared minus 4ac, all over 20. Okay, so we want to try to simplify square root of 359. Okie dokie, and that, you can try to divide that and see if 359 breaks down, but I went through and tried to divide. 3 doesn't go in evenly. 5 doesn't go in, 7 doesn't go in, 9 doesn't go in. I kept trying more and more numbers, but I couldn't break it down. So we're going to leave this as negative 1 times square root of 359. Okay, so in other words, we have 1 plus or minus square root of negative 1 times 359. All over 20. And remember, when you have square root of negative 1, that becomes I. So I have 1 plus or minus square root of 359 times I, all over 20. If I were to write this in our complex number form, a plus bi, I'd separate this fraction into two fractions, 1 over 20 plus or minus square root of 359 over 20 times I. Okay, number 10 said describe the relationship between the answers you got for each of the equations above. Okay, looking back, let's look back at these answers. Right here, I had these answers. If I were to separate these out, that's like saying 1 over 20 plus 3 square root of 359 over 20 times I, and 1 over 20 minus square root of 359 over 20 times I. These are conjugates of each other. Remember the word conjugates we talked about yesterday. One is positive, one is negative between the terms. If you look back at the previous one here, the same thing would happen. You'd have negative 3/8 plus square root of 31 over 8 times I, and negative 3/8 minus square root of 31 over 8 times I. In both cases, the answers are conjugates. They always come in conjugate pairs. The complex zeros always come in conjugate pairs. They are conjugates of each other. Okay, so whenever you have solutions that are imaginary, they will always come in conjugate pairs. So sometimes you will be given answers, the solutions, and we want to know what was the equation that gave us those solutions. These are our given zeros or our given solutions, and they're asking us to write a quadratic function in general form that would have these solutions. So we want to work backwards to get our equations. If we know the solutions, we should be able to write our equation in factored form. If this is my zero, then the factor that would give me that zero would be x minus 3i. Because if this is positive 3i would make this equal to 0. And the factor for this 0 would be x plus 3i. So first, you're working backwards, so first write it in your equation in factored form. If I were to solve for x, these would be my zeros, right here and here, okay? So if I want to write this equation in general form, I'm going to need to multiply these factors out. So I would make a box and write these terms out on the outside, x minus 3i times x plus 3i, and multiply them together. So we get x squared in the first box. X times negative 3i is negative 3ix. And this will become positive 3ix. And the last one will be negative 9i squared. Okay, if you write out these boxes, you have x squared minus 3ix plus 3ix minus 9i squared equals 0. These two terms are opposite, and they're like terms, so they cancel each other out. The I squared equals negative 1, so this is equal to, this will end up multiplying to equal positive 9. So you get this equation, and that is in general form. Okay, we do the same thing over here. We have x minus this 0. That's the factor for the first one. And the next one will be x minus the other 0. So first write your equation in factored form. Then we want to multiply these factors together. And notice I have 3 terms here, so I'm going to make a 3 by 3 square this time. So if you multiply this out, you get x squared minus 3x. X times I is xi. Second row, we get negative 3x, positive 9. Negative 3xi. Third row, I get negative ix, positive 3i, and negative I squared. Okay, so then I'm not going to write out all 9 terms because we can combine some of these as we go. I don't have any other x squared, so I'll write that down. Okay, I'll cross that off. Negative 3x and negative 3x are like terms, so when you add them together, you get negative 6x. Okay, the positive xi and negative ix are like terms. They're opposites, so you can cross those off. They cancel out. Sorry, this box here should have been negative 3i, not negative 3xi, just negative 3i. So you have another negative 3i and a positive 3i. These should have canceled out. And you have positive 9, so plus 9. And you have negative I squared left. Okay, equals 0. Okay, keep in mind I squared equals -1, so we're subtracting -1 here at the end, which is really like adding 1. So we get x squared minus 6x. 9 plus 1 is 10. And that will be your solution. X squared minus 6x plus 10 equals 0. So there is a quadratic function. Or you could write it in terms of f of x equals x squared minus 6x plus 10. Okay, this last part, look at the next page here. There's a table that shows all the different kinds of solutions you could have for a quadratic formula. Study it for a minute and then summarize what you see. So if we look at this, I'm going to just shrink it down so we can see the whole thing. If you look at the first column for x squared minus 2x plus 3, you'll notice that when they did quadratic formula and simplified their answer, they got two real numbers, -1 and 3. There was a positive number inside the square root. That's our discriminant right here. b squared minus 4ac produced a positive number 16. And we ended up with two real solutions. Notice those are your x-intercepts, -1 and 3, two distinct ones. In the second equation, when you did the quadratic formula, you had a 0 under the square root, which resulted in one real solution. We call that a repeated solution. Your answer was 3. This occurs because if you think about the factored form of x squared minus 6x plus 9, if you factored it, you would get x minus 3 times x minus 3. Okay? You get a repeated factor, a repeated solution. That's why I call it a repeated x-intercept. In the third one, notice when they do quadratic formula, we had a negative number under the square root, which resulted in two complex solutions, two solutions with an imaginary number. And notice when that happens, you have no x-intercepts. So x-intercepts only happen when your answers are real numbers. So number 13 says, find the discriminant for each of the equations in the table. Remember, discriminant is equal to b squared minus 4ac. That's the number under the square root. So the discriminant for the first equation is 16. The discriminant for the second equation is 0. And the discriminant for the third equation is -3. So how can we use the discriminant to determine the number of solutions? If the discriminant's a positive number, we would say that it has two real solutions. If positive, that means it's two real solutions. If it is 0, if it equals 0, then there's just one real solution, one repeated solution. If your discriminant is a negative number, you have no real solutions, no x-intercepts, so you'll have two complex or imaginary solutions. And that's it. Your assignment is to go on and do the complex number and quadratic formula day 2 assignment on the next page of your packet. Have a great day.